Lesson 34 deals with this idea of implicit differentiation, and we'll explain what that is. First of all, let's talk about explicit equations. Those are equations with a y equals or f of x equals, and there's no y's on the other side. So you know what y equals explicitly. Implicit equations then are any other form of the equation where you might have x's and y's multiplied together or on both sides of an equation. So not all equations can be written explicitly, so we have implicit differentiation. Up until now, we've always differentiated if it was in explicit form. So we're going to have a process here that helps us with implicit equations. So what we're going to do is differentiate each term, divide both sides by the desired differential. So that means if we're trying to find like dy dx, we're going to divide everything by dx, and you might do that by dt. It just depends on your variables. And then solve for the desired derivative. So you're going to get all the terms with the derivative that you want on one side and everything that doesn't have that derivative you want on the other side. So let's jump into it. Here's our first one. Notice this is an implicit equation. We have x's and y's on both sides. Now this one we could solve for y and then differentiate from there, but it's going to be easier just to do implicit differentiation. So our first thing we're going to do is we're going to differentiate each side or each term. So this is a product rule. So we want to do first, so x times the differential of the second, well that's just 1 dy. So again, product rule, first times the differential of the second plus second times the differential of the first, plus the derivative or differential of 1, which is just 0. So we'll put it in there just so we remember we worked with that. And then on the other side, the differential of 2x is 2 dx, and the differential of negative y is negative dy. So there we differentiated both sides or each term. And now what we want to do is we want to divide by the differential we're looking for. So we're going to divide both sides by dx. So divide everything by dx. Don't really need to work with this 0 here because it's nothing. And so when we do that, dx's cancel here, and they cancel here. And now we want to solve for the desired derivative. So what we're going to do is we're going to get anything with dy dx on one side. Let's write this out a little neater. So this is x dy dx plus y equals 2 minus dy dx. So again, we want to get things with dy dx on one side and things that don't have dy dx on the other side. And so let's do that. We will subtract y from both sides, and at the same time we'll add dy dx to both sides. Which gives us x dy dx plus dy dx. Now as you get better at this, you're going to probably be able to skip a few steps here and write what the answer might be. And then we have 2 minus y over on this side. And then we factor out what we're trying to find. So we got the dyx in common. What's left? Well, an x plus a 1 equals 2 minus y, and then finally we can solve for dy dx by dividing both sides by x plus 1. And so our answer is dy dx equals 2 minus y over x plus 1. And so there's our first one where we solved by implicit differentiation. The next slide just points out or shows us that we can solve for different things. So here we're solving for dy over dx, which is our normal thing, dx over dy, and then dy over dt, which there's not a t involved up here, but we can still divide everything by dt. That actually a lot of times has to do with time, a change in time. So this would be used in maybe some physics type problems. So here we have, given that y squared minus xy equals sine x, and that both x and y are functions of time, find these three things. So we're going to use implicit differentiation. So let's go ahead and write our original y squared minus xy equals sine x. And again, we're going to differentiate each term. So this is 2y dy minus, and we have a product here, so we have to be careful to use the product rule. And I am going to put this in parentheses because this negative is going to be distributed to these couple terms. So first, times the differential of y, which is just 1 dy, plus second, y times the differential of the first, which is 1 dx. And then equals, differential of sine x is cosine x dx. We'll distribute our negative before we go on to the next step. So we sometimes have to do some simplifying first of all. So minus x dy minus y dx equals cosine x dx. Now let's look back up what we want to find. We want to find dy over dx. So we're going to divide everything by dx. And when we divide both sides by dx, on the left side, it's a common denominator, so we can write these as individual ones. So we have 2y dy dx minus x dy dx plus y, or minus y, because the dx's would cancel. So dx over dx equals cosine x, because the dx's cancel. Now what we would do is we have dy dx is over here already. We're going to add y to both sides. And as I write this next step, I'm going to go ahead and factor out the dy dx at the same time. So this becomes 0. And we're going to factor out the dy dx. Well, not equals. We got 2y minus x equals cosine x plus y. And then to finish it off, we would divide both sides by 2y minus x. And finally, we get our answer of dy dx equals cosine x plus y over 2y minus x. And there's dy dx for that function. The next one, part B, we want to find dx dy. Well, we could start off the same way. Here's the original. We differentiate each part. The part where it would change then is instead of dividing everything by dx, we would divide everything by dy, and then we would solve from there. Except there's even a better way to do this. If you already know dy dx, remember these are differentials, so you can work with algebra and use the rules of algebra with them. So dy over dx, if I want to find dx over dy, it's just going to be the reciprocal of that. So the reciprocal. So we had to do pretty much no work at all here. So we have 2y minus x over cosine x plus y. And that's our answer. Now, we would have had to go through the work had we not had part A, but if you do have part A, you can just do the reciprocal. And the last one, dy dt. Again, we would start off the same way. We have our original. We differentiate each part, and then this next blue part here, that is the negative distributed. So I'm going to just start there. So we have 2y dy minus x dy minus y dx equals cosine of x dx. So all I did was take this blue part right here and rewrite it, because those first few steps are the same. The different part is we need to divide both sides by dt this time, because we're finding dy dt. Still going to look very similar, and we probably could have talked through it, but let's just do the work anyway. So now we have 2y dy dt minus x dy dt. And we'll see here, we don't have anything canceling. We just have y dx dt, and then cosine of x dx dt. So we have these fractions in each term this time when we divide by something different, dt. The steps remain the same though. You want to solve for whatever you're looking for. We're looking for dy dt, so we'll get anything with dy dt on one side and anything that doesn't have dy dt on the other side. Well, these first two terms both have dy dt. This one does not, so we're going to add that to both sides. So that's a dx dt. And in this case, this becomes 0. Over here, we have a dy dt in common, so we'll go ahead and factor out the dy dt. This is going to be 2y minus x. On the left side, we both have dx dt, so we can actually factor that out now. Cosine x. So let's go back. We'll write dx dt. We will do some moving around here shortly, and then times cosine x plus y. And now we'll divide both sides by 2y minus x, because we want to get this by itself, this dy dt by itself. And let's finish this up. We got dy dt. That's what we want on the left. This cancels. Equals, and we're going to just write this a little bit differently. This dx dt we usually write at the end if there's something left. So dx dt, and then cosine x plus y over 2y minus x. And so what we see here, we've solved dy dt, and we would say we solved it in terms of another derivative dx dt. So that's interesting, and that will come up later as we work through different types of problems. Let's take a look at this one. What's dy dx? Well, we'll do implicit differentiation. Notice we have two product rules here on the left, so we need to be careful with that. First, so x squared times the differential of the second, which is 1 dy, plus second, which is y, the second term, times the differential of the first, which is 2x dx. Now we have this subtracted. Well, I'm going to put a subtraction, and I'm going to put parentheses so we know to distribute the negative. Again, we have first times the differential of e to the x, which is just e to the x dx. And then second, e to the x, so plus e to the x times the differential of the first, which is just 1 dy. And then on the other side, we have the differential of cosine x, and that is negative sine x dx. We'll distribute the negative. So we have x squared dy plus 2xy dx. Distribute the negative. This is minus y e to the x dx minus e to the x dy equals negative sine of x dx. So again, we are trying to find dy dx, so now we will divide everything by dx. I've been putting it under everything and then doing this, but it's sometimes easier just to put the dx. It seems like, well, you're writing dx a lot, but putting dx under everything first, because then we can just see what cancels. So these dx's cancel, and we can go ahead and subtract right away. So we're going to subtract this term. So minus 2xy from both sides. And we'll also add this term to both sides, y times e to the x. I think that will do it. So you can save some time by doing things a little bit differently. Now notice that we have x squared dy dx. So these are gone, gone, gone. Minus e to the x dy dx, so we can actually factor out the dy dx. So we have dy dx times x squared minus e to the x equals, over here, we have three terms. I'm going to put the positive one first. So y times e to the x minus sine x minus 2xy. And then to finish it off, we need to divide both sides by x squared minus e to the x. And our answer is dy dx equals y times e to the x minus sine x minus 2xy over x squared minus e to the x. And there you have the differential, or the derivative dy dx of x squared y minus y times e to the x equals cosine of x. The things to be careful with that I see mistakes some people forget to do: the product rule, or in this case, sometimes they forget to distribute the negative. The last few slides have to do with this same equation that we'll be talking about. It says find the slope of the tangent line to the graph of x squared plus y squared equals 2 at the point 1, 1. So what we want to do is we want to find the slope of the tangent line. The slope of the tangent line really just means we want to find the derivative of this graph at 1, 1. Now it does help you. You actually don't need to know this to do the problem, but it does help to know that this is a circle centered at the origin with a radius of the square root of 2. So we're going to be looking at 1, 1 here. So it's telling us 1, 1. So it would be right there on the graph. Just by looking at this, we could probably take a guess. That's like right in the middle of the graph of this circle there in the first quadrant. It's probably going to be -1. If you see that tangent line coming through here, looks like a slope of -1. So that's our guess. So understanding what you're actually looking for is helpful. But we can do this with calculus. And so we want to find the slope of the tangent line. Well, that's the derivative, so we're going to be looking for dy dx. Well, we want to find dy dx. We want to find the derivative of this. X and y are both on this side. We could solve for y, but let's go ahead and differentiate implicitly. So we would do the differential of this, which is 2x dx, plus differential of this is 2y dy, and the differential of 2 is just 0. And now we want to find dy dx, so we could divide everything by dx. Which this cancels. We could subtract 2x from both sides, which means this is gone. And we have 2y dy dx equals -2x. And to finish it off, we would divide both sides by 2y. And we see that the 2's would cancel, and we get -x over y. So dy dx equals -x over y. Well, it is asking for this at this specific point. So there's a whole lot of points that go around this circle. It's asking for 1, 1. So we would put 1 and 1 in. So this is where we could use this notation. So at the point 1, 1. And that would be negative. And we put 1 in for x and 1 in for y. And we do get -1. So an understanding of the graph was very helpful there. So keep this in mind as we go on to the next ones, because they do relate to it. Our derivative was -x over y. Let's see what these say. Find the points on the graph x squared plus y squared equals 2 where the tangent line is horizontal or the tangent line is vertical. Well, once again, having a good understanding of what this graph looks like is going to make this really easy for us. When is the tangent line horizontal? Well, it's horizontal up here and down here. What points are those? Find the points. Well, this top point is x is 0. And how high is this? Well, remember, I think I mentioned it before, but this means the radius isn't 2, it's the square root of 2. So 0 squared of 2, there's one horizontal tangent line, and then there's another one below at the bottom, which would be 0, -√2. Vertical tangent lines, let's do these in red, they would be here and here. And what points are those? Well, that's at √2, x is √2, 0, and -√2, 0. And there's your answer for those. You could do them with calculus. We could take the derivative that we found from the last slide. So this all does work together. You have the graph and can use that, but you can also figure this out. To find when it's horizontal. Horizontal is when the slope is 0. So what we would do is we would take this equation. So we already found our answer, but I'm showing if you had to do it using calculus, you would put 0 in for the slope for dy dx equals -x over y. And you think, well, how could we get 0 here? How does a fraction equal 0? Well, a fraction equals 0 when the numerator is 0. So x would have to equal 0. You know x equals 0, you would plug that back in to find the corresponding y values. So put 0 in for x, so 0 squared plus y squared equals 2. This is just 0. We could take the square root of both sides. Y equals plus or minus the square root of 2. And so our points are when x was 0, y was either equal to positive root 2 or negative root 2. You can actually write it like this, where you put 0 plus or minus root 2. Similarly, we could come over here, wasn't supposed to cross that out, and think, oh, let's think of the slope again. dy dx equals negative x over y. This time, we want it to be a vertical tangent line, so the slope would be undefined. Well, thinking here, what has to be true about a fraction for the slope to be undefined? Well, the denominator has to equal 0, so y would have to equal 0. And then you take that 0 and you plug it into this equation, and you would put x squared plus 0 squared equals 2. This is 0. You take the square root of both sides, and you get plus or minus root 2 again, which this time you could say plus or minus root 2, 0, your x values and your y value. So 2 ways to do it. Obviously, in this case, the graph was much easier. We got our answer quickly, but maybe that's not always the case that we can do that. Still the same equation, find dx dt, and we see here that these are both functions of time. So find dx dt, well, we take our original equation and differentiate, so 2x dx plus 2y dy equals the differential of 2 is 0. We want to find dx dt, so we're going to divide everything by dt. And we get 2x dx dt. We'll subtract this from both sides, 2y dy dt. And that gives us negative 2y dy dt. And then we divide both sides by 2x. We get something similar to what we saw before, except we have the dy dt in there. So dx dt is equal to, the 2's will cancel, so it's negative y over x dy dt, and there we have it. That's what they asked for this first one. Part B says you want to find dx dt at 1, 1 when dy dt equals 7. So notice here, when you solve for dx dt, there's a dy dt over here. So we found dx dt in terms of dy dt. And so instead of just plugging a point in like we were able to previously, where we were just able to plug in the 1, 1, we needed more information because we need to know what goes in for this dy dt. So now all we do is plug in 1, 1 and dy dt. So dx dt equals, put in 1 for y, and 1 for x, and 7 for dy dt, and we get for part B, that dx dt is -7. And that is implicit differentiation